All right, so we should be live. Here, hang on 1 second. Alrighty. Oh my. So we had a little bit of difficulty establishing yeah, a steady stream, but we got that situation stabilized, and currently you can hear my 18-month-old in the background. So oh, hang on 1 second. I'm getting some audio feedback. All right. So my apologies for being late. I'm actually setting up in a different location on what did I say? Wednesday. On Monday, I actually set up from campus um, um, to kind of so I could be there to show kind of other faculty the setup I was using. Today is my first day broadcasting from home. So if you you know hear a baby or other humans, that's where that's coming from. Why did I spell hello with a W? This is my biggest question right now. I'm naturally not a good speller, but when under the gun, it goes by the wayside rather quickly. Um, our song of the day. Our song of the day is "Bright Mississippi." And I still can spell Mississippi. Um, by Thelonious Monk. Trying to generate kind of chill vibes this morning, so we were listening to some jazz. Okay, so here we are. Um, 10 minutes late, but diving in nonetheless. So let's grab. Oh, goodness. Hang on, Windows is spazzing out on me a little bit here. Okay. There we go. Okay. Technical difficulties. Whoa. Should be resolving. Okay. All right. Choppy start to day 2 of digital instruction. We should be finishing up chapter 6 today. Oh, hey, Macy. And should be finishing up chapter 6 today, and we will most likely be diving into chapter 7. Before we get going, though, I wanted to just mention a few things. Oh, goodness. So before we get going, just a couple things by way of announcement. So I know I made I posted on Canvas last night, and if you haven't had a chance to look at that, all this information is there. But a couple things structurally. So we will be doing lecture at our normal appointed time, but in addition, I'm going to be starting. Oh goodness. Friday office hours. So we're going to be having. I'm going to be hosting an office hour every Friday at 1. And the purpose of this is so I've received a lot of emails asking questions like, okay, this homework problem, that homework problem, and these are the things that I normally answer through in lecture, after lecture on the whiteboard, or before lecture gets going. And it's possible to answer them over email, but it's just much better with a whiteboard. So I'm going to be holding office hours, and so that you can email me questions throughout the week, and I'll be answering them and working them in a live stream, so you can tune in live if you want, or rewatch later. I'll try to answer all of them as best I can. I'll also be open to taking live questions as well. I'll give priority to the ones that have been emailed in. But anyways, this is just a way of kind of figuring out how to continue instruction in this kind of new digital world. So email me your questions. In addition, sorry. So email me your questions. If you could use the subject Chem 400 office hours. That would be super helpful for me. That way I can find them. Again, the email inbox is just constantly being inundated by updates. So of the fact that we're still under a pandemic. So if you use this subject line tag, it'll be helpful for me, make it easier for me to find it, so to make sure your questions don't get overlooked. And also, you can interact with me on the Aromatic Asthmatic Facebook page. Again, this is just another way to connect. Also, the Facebook page is not being inundated by updates from my colleagues, not your colleagues, your other professors. So this might be a more direct and streamlined way to interact. Also, it's a public forum, so if you have a question, guaranteed there's at least 3 other people in the class who do. So it might be a way to reach more people at once, and we can interact with each other. I don't know, trying things. Want to know what you guys think. I have a question in the comments from Sulai. Hey, Professor, I was wondering how we submit exercise 7. So the lab exercises, how you submit the lab exercises is totally up to your lab instructor. So I would get in contact with them. They may want you to scan an email. I'm not exactly sure how they would want you to submit them. I know that's how I would want you to submit them if I were a lab instructor. But it's totally up to them. So I would ask for all the lab assignments, how they want that to be submitted. All right. Okay, so that is all the business end of things for this moment in time. I'd like to start by actually doing a another problem. Oh goodness. Okay, hang on. I have to fix the keyboard setting because okay, I thought I had, but now my apologies. The screen's gonna go crazy for a hot second. Okay. There it goes. Getting all gnarly. Okay, so I'd like to start with a problem involving Hess's Law, like the one that we did yesterday. All right, and in this problem, we want to calculate the change in enthalpy for the following reaction. The reaction between dicarbon tetrahydride, that's ethylene, reacting with oxygen gas to produce, this is another combustion reaction, carbon dioxide. Oh wait, hang on. That's not the reaction we want to calculate. We want to be calculating the reaction of ethylene, C2H4, its reaction with H2 gas, hydrogen gas, to produce C2H6, which is ethane or dicarbon hexahydride. And we want to do this, we want to calculate this from the following data. So we have the combustion of ethylene, C2H4 plus O2, producing carbon dioxide and water. All right, and this chemical equation, when balanced, has 3 oxygen molecules, 2 carbon dioxide molecules, and 2 hydrogen molecules. Our delta H here is negative 1411 kilojoules per mole. All right. The second reaction we're given is a reaction between ethane, C2H6, and oxygen, another combustion reaction. Produces CO2 and water. Oh, sorry. In this problem, they're giving the phase of water is liquid water. Our delta H here is negative 1560. That decimal means that we have 4 sig figs we're dealing with. Kilojoules per mole. Finally, we're dealing with H2 plus 1/2 O2, producing liquid water. And the delta H for this reaction is negative 285.8 kilojoules per mole. Okay, here, hang on 1 second. I'm going to put this stream on. Alrighty, sorry about that lag. Okay, so we are back. We have, again, this is a Hess's Law problem. So we need to calculate the delta H for this reaction. We have a target reaction that we need to calculate our change in enthalpy for. And just like last time, we have 3 different species that we need to place in this reaction. We have 2 reactants and a products. And so what we need to do is find those specific reactants and make sure that they are placed in the correct side of the reaction, either the products or reactants. And we need to make sure that they have the correct stoichiometric coefficients. So with this first, our first reactant, C2H4, that's in our first reaction, and you'll notice that it is both on the product side and it has the correct number of stoichiometric coefficients. Okay, hang on one second. Okay, so I have a question. Is it okay to have a fraction for moles in front of the oxygen? Yeah, you'll notice that in 2 places here, both for the second and third reaction, we have 7 halves O2, and then we have 1/2 O2. In some problems that you work in your homework, they'll be given to you, the equations given to you will have fractions in the stoichiometric, for the stoichiometric coefficients. And if they're given to you, that's fine. It's not okay to have that in your final answer, but as we'll see, this will all cancel out in the end. All right, so for our first reaction, we're going to write down C2H4 plus 3 oxygen molecules produces 2 CO2 molecules plus 2 H2O. And this has a delta H of negative 1411 kilojoules per mole. So we have our first species taken care of. All right. Now when we move on to our second species, H2, we're going to go to our second reaction. All right. Now when you look, sorry, not our second, I said second, our third reaction. Our third reaction has H2. Actually, I'm going to write this directly into kind of our final sheet here, because our third reaction is a reaction of hydrogen gas plus 1/2 of a mole of oxygen gas, producing 1 mole of liquid water. And you'll notice that our second reactant here, again, is on the correct side of the reaction and has the correct stoichiometric coefficient, so we don't need to manipulate this at all. We can just write down our delta H, which is negative 285.8 kilojoules per mole. All right. Our third and final species that we need to place, right, our C2H6, that is in the second reaction. But you'll notice, and here we need to pop to a new slide, that it's on the wrong side of the chemical equation. The equation that we're given was C2H6 reacting with O2. Let's see, 7 halves of O2, producing carbon dioxide and H2O. And our delta H here was negative 1560 kilojoules per mole. Ooh, gets a little squished on the side. But the problem here is we have our product, C2H6, on the reactant side. So what we need to do is we need to flip our products and reactants. And whenever we do that, our change in enthalpy gets multiplied by a -1. So rewriting this equation, again, flipping it, we'll have 2 moles of CO2 plus 3 moles of H2O producing 1 mole of C2H6 and 7/2 moles of O2. And here our delta H will be a positive 1560 kilojoules per mole. All right, now that we've placed all of our reactants and products, we need to make sure that all other species in this reaction cancel so that we're just left with ethane, hydrogen, and ethylene. So first off, we have carbon dioxide and water. And if we look at it, we have 2 moles of carbon dioxide on the reactant side of our third equation, 2 moles on the product side of our third equation. So those two cancel. We also have water to deal with. And here on our reactant side, we have 3 moles of water. And on our product side in the first equation, we have 2. On the products side of the second equation, we have 1. So that 3 will cancel, the 3 on the reactant side will cancel the 3 on the product side. Finally, we have to deal with oxygen gas. And we have 7/2, which is also 3 1/2, right? That will cancel the 3 moles and the 1/2 mole of oxygen. So it kind of a very lengthy answer to Ryan's question. Is it okay to have the halves as long as they all cancel out by the end? And in this case, they do. It is totally okay to have fractions in your balanced chemical equation while you're working a problem. So here we have C2H4 plus H2, these two reacting to make C2H6. And our change in enthalpy for this reaction, now we got to crunch some numbers, is going to be, let's see, negative 1411 minus 285.8 plus 1560. So my answer, my value is negative 136.8. But when we look at our significant figures, you'll notice that 1400 and 11 is precise to the ones place. Same with 1560. So our answer must be precise to the ones place. So that 8 is going to round our 6 up to a 7. So 137 kilojoules per mole. All right, so that is the final answer And again, we've used the principle of Hess's law to take three combustion reactions and determine the delta H of a reduction, actually, a reaction between ethylene and H2 to produce ethane, a much harder reaction to study. Cool. Any questions on the situation? All right. So zero this and this. Now, this is not the only application of Hess's law. Hess's law has many applications. We're going to look at a second one here, and then actually we'll see it circle back around later when we look at Lewis structures, and we'll talk about bond enthalpy of formation. Not bond enthalpy of formation, bond dissociation energy. There we go. So, another application, and I would argue the most useful application of Hess's law. Again, remember, Hess's law says that enthalpy is a state function. It's therefore independent of path. It does not matter how we calculate enthalpy. All that matters is that we get there. And probably the most important application of Hess's law comes into play with something called the standard enthalpy of formation. Standard enthalpy of formation. All right. The standard enthalpy of formation is represented with the symbol delta H naught F. The naught, here, this little circle tells you that you're under standard conditions, so that's where the standard comes from. The F is because we're talking about formation reactions. And to understand how to use standard enthalpy of formations, we need to be familiar with a couple principles. First, we need to know what a formation reaction is. All right, so formation reactions. A formation reaction is defined as the formation of 1 mole of a compound from its constituent elements in their standard state. All right, the formation of 1 mole of a compound from its constituent elements in its standard state. All right, it's the most kind of basic reaction out there. You have all your individual elements in a compound. They react to form that compound. This is often called the Voltron reaction because it's how Voltron forms from all its constituents. LOL robots. All right. Now, the key to understanding what a formation reaction is, or one of the key things to understanding the implications for this, for the standard enthalpy of formation, is knowing what is meant by standard state. All right. So when we talk about standard states. When we were talking about a gas in its standard state is a gas that has a pressure of 1 atmosphere. All right. A liquid. Wait, hang on. Yeah, a liquid or solid in its standard state, or in their standard states, are stable at 1 atmosphere and 25 degrees Celsius. All right, so a liquid and a solid in its standard state is stable at that temperature and pressure. And then for aqueous, an aqueous solution in its standard state has a concentration of 1 molar. All right, so that is the definition of the standard state for anything, any phase, gas, liquid, solid, or aqueous phase. Now, in addition, so we need to go to a new slide. In addition, there's one last piece of information that you need before we can start talking about using standard enthalpy of formation, and that is a pure element in its standard state has its lowest possible energy which means that it has an enthalpy of 0. Zero kilojoules per mole. All right, a pure element in its inner state has its lowest possible energy, because you think about it, an element's not a compound, right? An element is just the atom sitting there. I guess I shouldn't say an element's not a compound, right? We have H2 as a molecular element, but it's still, even for H2, the simplest form it exists in. And when it's in its standard state, it's at its lowest possible energy, right? So consider, for example, the following reaction. Let's consider the formation reaction for carbon tetrahydride or methane. This involves a reaction between solid carbon and hydrogen gas. Oops, why did I put an equal sign there? And it produces CH4, carbon tetrahydride. All right. We need 2 molecules of H2 to complete this reaction. This is a formation reaction because we're producing 1 mole of our compound. Now, consider the delta H for this formation reaction under standard conditions. Now, we all know what delta means, right? It means final minus initial. So our final state would be the delta H, not the delta H, would just be the pure enthalpy of the products minus the enthalpy of reactants, right? Which, for this reaction, means the change in enthalpy of this formation reaction is equal to the enthalpy of CH4, right, minus the enthalpy of solid carbon plus 2 times the enthalpy of our H2 molecule, right? Now, this might seem a little weird because we haven't talked about enthalpies at all. It's always been the change in enthalpy. And here, you'll notice that we have change in enthalpy is equal to the enthalpy of our product minus the enthalpy of our reactants. Now, here's where things get interesting. You'll notice that both carbon and hydrogen are elements, pure elements, in their standard state. That means that the enthalpy of carbon is 0 and the enthalpy of hydrogen is 0. With both of those terms zeroing out, that tells us that the delta H of this formation reaction is simply equal to the enthalpy of CH4. All right, and here's where this pays dividends. Here's where this becomes super useful. It's very hard to measure the absolute enthalpy of substances. We can measure the change in enthalpy for a reaction, but the absolute enthalpy for individual substances is a difficult quantity to measure. But because we know that a pure element in its standard state is at its lowest possible energy, and therefore its absolute enthalpy is 0, that means that the change in enthalpy for a formation reaction actually equals the change in enthalpy for that, or the absolute enthalpy for that compound. We can therefore use the measured change in enthalpies of formation reactions to calculate delta H for compounds by looking up the individual formation reaction enthalpies for each molecule in a reaction. All right, that was a mouthful, and I think I just said nearly 1,000 words, but we all know that that's worth one picture. So let me illustrate for you how this actually comes into play. Let's look at the reaction between methane, CH4 gas, plus 2 moles of O2 that produce carbon dioxide gas and water. All right, this situation is now balanced, and we want to determine what the delta H of this reaction is. All right, now, before this moment in time, whenever we'd see, okay, find the delta H for a reaction, we'd instantly look for, okay, they're going to give us, I'm going to give you some sort of system of equations, right? And you're going to have to find, okay, where's my methane, where's my O2, where's my CO2, where's my water, and arrange it accordingly, manipulate the reactions, add them all together, calculate a delta H. So in this instance, we don't have to do that. We don't have to rely on a system of equations because we have this little circle here. We have this little knot. This means that we're under standard conditions This means we're under standard conditions, and we need to, that allows us to use change in enthalpy of formation. All right. Now, in your book, in chapter 6, there's going to be a table that has a bunch of different compounds. So like CH4, CO2, we'll be able to find all of these here. And H2O. And then it'll list their enthalpies of formation for each of these compounds. All right, so you can actually look all these up. Whenever it tells you, when you're working homework problems and they ask you to calculate delta H of formation, but they don't give you, not calculate the delta H of a reaction using the delta H of formation, they're expecting you to look up the table with all these values. All right, and these values are all going to be in kilojoules per mole. The delta H of formation for methane is, let's see, where we go, 76.4. Delta H of formation for, that's a negative. Delta H of formation for carbon dioxide is negative 393.5, and then for water is negative 241.8. Okay, sorry. Question. So do we have to memorize the enthalpy of formation? You absolutely do not have to memorize these. I'll provide them for you in a testing context. So no, you don't have to have these memorized. You just need to know how to look them up. Good question. One thing to be careful of when you're looking them up is phase matters. When you look up the standard enthalpy of formation reactions, you'll notice that water actually shows up twice. Water actually shows up twice, and that's because the enthalpy of formation for liquid water and water vapor are actually different. So if you're doing a homework problem on your own and you're like, oh sweet, this one's kind of easy, you do it, you get the wrong answer, double check to make sure that you have the correct phase, because these actually have different values. All right, let's see. Oh. You know what's fun? So Ryan just pointed out, my textbook shows the change of enthalpy of formation for methane is 74.6. And you know what's interesting, Ryan, is that's what my notes show too. Dyslexia makes life more exciting. And it's a way of testing to see if your if your students are actually watching your lecture. Thank you for that catch. 74.6. Okay, now here's how we apply this. Your delta H for your reaction under standard conditions will equal the delta H's of formation of your products, because that's the final form, right? Minus the delta H of formation of your reactants. Let's see. So this is the equation that you're going to come back to. Now, here we have two products. Oh, Ryan. Oh, dude, thank you for being that guy. Actually, it will make things less confusing for everyone in the long run. Totally. So here, we've got two products, right? One, we have carbon dioxide, which has a change of enthalpy of formation of 393.5. This is kilojoules per mole. All right. plus our change in enthalpy for water vapor, which is negative 241.8 kilojoules per mole. All right. Now, when you are plugging in your values, excuse me, got the hiccups here. One thing you have to be very aware of are your stoichiometric coefficients, because the definition of the change in enthalpy for a formation reaction is 1 mole, right, of compound forms. Excuse me. 1 mole of compound forms. So because we only produce 1 mole of CO2, we multiply that 393.5 by 1. However, because we're producing 2 molecules of water, we need to multiply that delta HF formation by 2. Right, and those are our reactants. And now we need to go minus the delta HF formation for our products. I'm going to scoot up or write my conditions smaller. There we go. Now, those are our products. Now we need to subtract our reactants. Now, the change in enthalpy of formation for methane is negative 70. There goes the dyslexia again. 74.6 kilojoules per mole. All right. Plus, now here, you'll notice that that I don't have O2 in my chart of change in enthalpy of formations. And if you look in your chart that your textbook has, your table of change in enthalpy of formation reactions, you also won't find O2. All right? And the reason that is because oxygen is a pure substance in its standard state. So it has an enthalpy of 0 kilojoules per mole. Right? Because this is a pure element in its standard state. So if you find yourself scratching your head like, oh, I can't find one of my reactants or products to finish this problem, to solve this problem, take a second look at it. It may be an element, which is why it doesn't show up in your table. All right. So now that we have everything lined up, we can crunch some numbers. We have the change in enthalpy for this reaction under standard conditions is equal to negative 393.5 kilojoules per mole. Minus, let's see, we've got 2 times negative 241.8. So that's negative 483.6 kilojoules per mole. And then we have a negative 1 times our negative 74, so plus 74.6 kilojoules per mole. And now we can add all these wonderful numbers together. 74.6, then minus. All right, I'm actually just going to double check that. Negative 393.5 minus 483.6 plus 74.6. All right, so my value that I'm getting is a negative 802.5. When we look at our significant digits, each one of these numbers that we added has its last significant digit in the tenths place, as does our answer, so we don't need to round. And our units are kilojoules per mole. All right, so that is the change in enthalpy for our reaction. Again, a lot simpler to use, a lot easier to use than using manipulating a bunch of equations and their delta H's to make sure everything adds and cancels. So it has a huge advantage, the standard enthalpy of formations, as opposed to the other method that we learned on Monday. The one drawback to using standard enthalpy of formations is the fact that your reaction that you're studying, you can only use standard enthalpy of formation if your reaction is under standard conditions. All right, so you can only use them if you're under standard conditions. So if you're wondering why would we ever use the other way, it's because not every reaction takes place at 1 atmosphere and 25 degrees Celsius, as we've already seen this semester. Cool? Okay. All right, that actually brings us to the end of chapter 7, if you can believe it. Oh, no, sorry, chapter 6. So we are about to dive in to chapter 7. And I've got to pull up a new set of lecture notes. All right. Any questions before we leave chapter 6 in our wake? All right. Okay. So, I guess that that we actually need a different title up here. We are going to start chapter 7, which is an intro to a very, very scary thing called quantum chemistry. So this word quantum is sounds terrifying. It usually is the we've all heard this word before. It's busted out in pretty much every science fiction movie that you can watch, and about every other Avengers movie bandies this word to explain the unexplainable. It sends Ant-Man on a trip through the quantum realm, which looked a lot more like like he's been doing the magic mushrooms than anything else. And it's so here's the thing. To actually talk about quantum chemistry and quantum mechanics, you need a lot more math and physics than are required for this course. So this is a very, very simplified, stripped down kind of introduction to some of the concepts that we introductory concepts to quantum chemistry. I've taken this class. I was a chemistry major and I took it as a senior, and in order to take it, the prereqs were a year of Gen Chem, a year of physics, actually 4 quarters of physics where I went, and 4 semesters of calculus. So clearly we're not at a position to truly understand quantum chemistry because we don't have enough calculus under our belt, and I'm not going to try to teach you calculus because that's not this course. So this is introductory. This chapter simplifies, and it flirts with oversimplification because we're doing the best we can with the math that's available to us. So anyways, it's we're gonna learn some concepts, but if this stuff is interesting to you, know that you're seeing the tip of the iceberg. The rest of it is submerged under an ocean of math and is more than enough to sink most of our Titanics. So that being said, to begin our discussion of quantum chemistry, we need to talk a little bit about light. Okay, hang on. Photoshop's being a little finicky for me. Okay, we need to talk a little bit about light. All right, now, so light. This chapter makes an assumption. We're going to make an assumption, and that assumption is light is a wave. Now, I'm sure that most of us are at least familiar with the concept of particle wave duality. And we know that sometimes it behaves like a particle. All right. Everything sometimes has some particle character and some wave character, including you and I, and even the planet Earth. And another thing that you'll learn is the degree to which something exhibits particle behavior versus wave behavior is determined by the amount of mass an object has. All right. And the larger the mass, the more particle-like it is. The lower the mass, the more wave-like it is. And the thing about light is light has no mass. Light has no mass, which means that it is the closest. It's almost a pure wave. It is the closest to being a pure wave. It's the closest to being a pure wave. It is the closest thing, I should say. Or I should say, it is... Oh, goodness. Here we go. This is why you don't revise sentences midstream, because you just end up erasing half of them. I should say, it is closer to being a pure wave than any other thing. So for the purpose of this chapter and this kind of intro to quantum chemistry, we are going to assume that light is a pure wave. All right. Now, a wave can be depicted as a sinusoidal function. This is driving me a little bit nuts here. Wait, hang on. Oh, there we go. Okay, sweet. My color picker in Photoshop wasn't working all of a sudden, and it was driving me crazy. All right, but now we're live. So you can depict light with a sinusoidal function, and there's some features of a light wave that you should be familiar with. So the measure from crest to crest or trough to trough, that distance is called the wavelength. All right. So lambda is a Greek letter. This is the wavelength. And it is an actual length. It's measured in meters or nanometers, centimeters, some distance unit. And you have another quantity that we won't really be using all that much in this class, but it's still worth pointing out. The distance from the baseline to a crest or a trough, this is called the amplitude. Right, so this is A is the amplitude. Oops, whoa. Holy moly. Oh, goodness. Okay, hang on. Oh, shoot. Okay. So this is the amplitude. Amplitude of the wave. And then finally, there's a symbol. This is the Greek letter nu. And U, called frequency. And frequency is difficult to depict. Frequency is a difficult quantity to depict by just looking at one singular wave. So I'm going to visually illustrate what frequency is on the next slide. Okay. I did a little faux pas here, drawing on my background, so I'm going to try to fix that real quick. There we go. I've lost my banner, but we'll survive for now. Okay. So now frequency. I'm going to illustrate frequency like so. So consider these two waves. Consider one wave who looks like this, and a second wave that looks like this. So here we have wave 1 and wave 2. All right, the definition of frequency is as follows. The definition of frequency, oh shoot. Hang on one second. I need to whip up a quick color palette. And then I need a red. We'll go this kind of salmon-y color. And now let's grab a green. Okay. Okay. Sorry about that strange interlude. Let's talk about frequency here. So frequency, the definition of frequency is as follows. It is the number of crests that pass through a fixed point in space a fixed point in space per unit time. All right. The number of crests that pass through a fixed point in space per unit time. Now, I want you to imagine that this is a snapshot. So as we consider wave 1 and wave 2, imagine that this is a snapshot of how wave 1 and wave 2 progresses, how they progress in 1 second. All right. If you look first at wave 1, and you look at the amount of crest that would pass through a point in space as it's moving, you see that we'd have a frequency of 2. All right. Now, when you look at wave 2, how many crests pass through? 1, 2, 3, 4, 5. So the second wave has a higher frequency. High frequency. The first wave has a lower frequency. Oh, why am I doing wavelength? Lower frequency. The second wave has a higher frequency because more crests pass. The first wave has a lower frequency because less crests pass through that point in time, or sorry, that point in space over the same time unit. Hopefully that makes sense. Now, yeah, it's totally a sine wave. Okay. Okay, so one of the things you'll notice, so we can see that wave 1 has a lower frequency, wave 2 has a higher frequency, but we could say the reverse is true. When I look at these two waves, and if I were to ask you which one has a larger wavelength, we definitely say that that wave 2 has a smaller wavelength, and that wave 1 has a larger wavelength. All right, that is because frequency and wavelength are inversely proportional. All right, frequency and wavelength are inversely proportional. So we can say that frequency is proportional to 1 over wavelength. That is what inverse proportionality means. And oh shoot, hang on. Oh man, I did it to myself again. Oh, okay, hang on, sorry. Losing my train of thought because the software is getting in the way. Oh, hang on. Okay. I'm just going to roll with this. All right, so frequency and wavelength are inversely proportional. That means, as I'm sure you've already started anticipating. Oh, hold on. All right. Oh wait, here we go. Okay, sorry. Photoshop froze for a second there. Okay. We should be good though. Yep. Okay. So as I'm sure you've already been anticipating, because not only have you seen this before, but we also had a technology lag, so things kind of shut down for a second. We can swap out this proportional to for an equal sign only if we substitute in a constant. Oops, hang on. Oh, shoot. So we can write frequency is equal to 1 over wavelength if we multiply one side of this equation by a constant. All right. Now, if we solve for our constant, wavelength cancels. We're left with the following expression. Frequency times wavelength is equal to this constant number, C, and I've got to get rid of these. Oops. Dots here. Oh no. There's some cool things about using Photoshop. There's some over a whiteboard, there's some downsides too, like your whiteboard will never freeze on you. So we just have to sit and be patient. Oh, here we go. It's coming back. Spazzing out. Come on, Photoshop. We really just want to finish this lecture. Oh, we're almost there too. My apologies. Oh. Okay. Wondering how bad this freeze is going to be. So, here's the thing. It's frozen in a semi-convenient place. You can see that frequency is equal to lambda times our constant C. Now, lambda has units of... Oh, you decided to come and play. Thank you. Okay. All right. We actually do get to finish this lecture. Lambda, as we know, has units. Oh, wait, hang on. Lambda has units of meters. All right, because it measures length. Frequency has units of per time. You'll notice that right here, per unit time. So frequency is measured in units of 1 over time. A very common one is seconds. All right, 1 over seconds. This unit actually has a name. This is called the hertz, Hz. And yet that is the same unit that's measured to a unit used to measure computing speed. So if you're like, oh, I've got a 3.6 gigahertz Intel processor, the reason why they use hertz is because they measure things in operations per second. How many operations can your processor perform per second time? It's a frequency unit. So here we have 1 over seconds times meters. That means this constant C has units of meters per second. This is, I think, super cool because this quantity here, meters per second, this quantity is a speed. Those of you with a little bit of physics in your background could probably catch that from a mile away. And that's because this is a speed, because C is something we call the constant speed of light. You may have heard that term bandied around a bit, like, oh, the time is the constant speed of light. But it's because the speed of light literally is constant. It doesn't matter what color of light, what frequency of light, what its wavelength is. Every single beam of light travels at the exact same speed. And that speed is C is equal to 3.00 times 10 to the 8th meters per second. You don't have to memorize that number. It's constant. I'll be providing it for you on your cover sheet with all your other equations. And so anyways, the constant speed of light, it's equal to the frequency of a photon of light multiplied by its wavelength, and it will, whatever that frequency and wavelength, whatever they are individually, it'll always come out to be 3.00 times 10 to the 8th. Okay. That, I think, is where we are going to wrap up lecture today. Again, I apologize for the later start time and some of the technical difficulties we encountered along the way. All part of discovering and navigating this new weird world we inhabit. I am totally down. I know some of you have to bounce. You have other online classes to get to. I'm totally down to hang for a little bit. If anybody has questions, I don't know if sorry, what am I trying to say? I don't know if anybody has any questions, or if you're all ready to peace out. But as always, I am very, very, very much interested in how your experience is. So please let me know what's good. Let me know. We'll go with a brick. Please let me know in comments or emails. Whatever. Let me know what's good. What needs help? So what needs work? Constructive criticism is super useful. Let me know what your opinions and ideas about resources. I'm totally interested in knowing like what resources would be useful, whether the resources that I'm providing are helpful. Like I said, I don't know if anybody's gone back to look at the previous video, but I put an outline in the description so that you can click to where each kind of segment of the lecture starts. Oh, thank you, Jake. That's very good to hear, that I'm handling this better than your other professors. So, and I'll be doing that with all the videos. So you can, if you're like, oh, I really wanted to just see like, where does that Hess's Law stuff start? So you'll be able to click on the link and it'll pop you to that place in the video. Also, as with the previous lecture, I'll be posting a PDF of the lecture slides, for you to go over, as well. So you can not only rewatch the live stream, but if you like studying by like actually looking at my sloppy handwriting as things progress, that'll be there and available for you as well. And again, this Friday, so in a couple days, we'll be doing our first kind of live stream office hour. So I've got a handful of emails about like homework question this or homework question that. One thing that would be super helpful, if you're still listening, and I may make a post specifically about office hours a little bit later today, but if you include maybe like snap a picture with your phone of the actual problem, if I can have everything in the email that I need to solve it, it'll definitely make it easier kind of organizing and getting everything together. That way, when it comes to doing the office hour on Friday, I won't be flipping through the textbook, but I can just have everything kind of collected. So that'll be an experiment. We'll see how that goes. Hopefully, that's another useful resource. And anyways, it's this is super weird. Oh, let's see. I think this is pretty solid setup. It's felt pretty smooth. Right. Okay, so one concern Ryan raised is he said it'd be great if you could answer the questions through email, if we're not able to do the Friday office hours. And here's the reason why I thought that would be a good kind of place to consolidate things is what I'm going to be doing in that kind of format is I'll be sitting down on YouTube working the problem step by step. So and talking through how to solve the problem. So even if you're not able to because I realize I just picked a random time on Friday. Actually, it's not random. It's 1:00 because that's when my wife normally works Friday, and my baby is napping at that time. So I know I'll be able to predictably, even if my wife's working, sit down and do a stream at 1:00 on Friday. But even if you can't tune in live for the stream, you'll get a step-by-step visual of me writing out the problem and the audio of me working the problem step by step that you can watch later, even if you're not able to tune in live. So I think that would be more helpful than a typed answer, because you actually get to see visually me work the problem and talk through. But we'll see. If we'll give it a try. If you're finding that maybe typed answers are more useful, I'm totally willing to do that as well. Another reason why I wanted to actually do the office hours too is for reaching a broader audience, because I guarantee if one of you has a question, there's a handful of students who are struggling with the same thing, and I think that publicly broadcasting the answers to those things, and again, I won't give away names, so you don't need to worry. If you're like, I'm afraid of asking a question because I don't want the rest of the class to know that I don't know how to do this, I will keep your identity private. So it'll just be an unknown student from an unknown class wanted to know this problem, and I'll do it. So please don't hesitate or feel embarrassed. There's no such thing as a stupid question, and guaranteed you're helping everyone out by allowing them to see kind of how to work that on their own. Cool. Other questions, concerns, things, details. Let's see. I know that I'm pulling up the syllabus right now. We are slated to take an exam sometime. I need to actually look at when that is. Here we go. Let's see, when's exam 2 scheduled? Oh, wow. Exam 2. It says that we're going to be taking exam 2 on Monday. Again, I will collect all this information into a post for later. But I will be pushing back the exam. I'll be postponing. So I can definitely say for now, I'm not going to be giving you guys the second test on Monday. It's been kind of a scramble to just get class live and digital. I still have a lot of exploration to do when it comes to what testing format or combination of formats I'm going to use. So I'll have more information, at least a date. I also need to look at where we are in lecture and figure out kind of where exam 2 should fall. But I will definitely be pushing that date back, and we'll have more information for you in a post. All right. I'm going to write this down. Exam 2 is only on 6 and 7. I will say this with my voice, but I'll also say it with my keyboard. Exam 2 is chapters 5 and 6 and part of 7. So we need to see, it depends how quickly lecture goes. The amount of 7 depends on our lecture speed. More info. More info will. Oh, can I spell will? It's a good question. Will come soon. Yes, so exam 2 will be chapter 5, chapter 6, and chapter 7. Chapter 5 is gas laws. Again, those were covered in lab lectures, but they will be a part of the lecture exam, specifically the combined gas law, ideal gas law, and Dalton's law of partial pressures. Chapter 6 will all be in there, and then some of chapter 7, as I said in that comment, it depends upon how much we how much of chapter 7 we cover in lecture will determine the amount that shows up on the test. Let's see. Okay. All right. Other questions. We still have 11 people hanging on here, listening to me ramble. I'll wait just a couple minutes. I'm gonna write down a note to myself for tonight's post. We got to do some exam 2 stuff. Exam 2 info, office hours info. Oh, you are welcome, Jesse. It's very nice. I have to say, you guys have been really awesome. It's been exciting to see, especially in the first lecture, the amount of students kind of like engaging, asking questions, even talking to each other. I think it's easier to. It takes a certain amount of. It's kind of nerve-wracking raising your hand in lecture and asking a question, and I've seen people talking in the live chat that aren't normal hand raisers, and so that's been really cool for me to experience. Hopefully it's been a decent experience for you as well. Also, you guys have been amazing as far as being nice to me and each other in a format that's probably I think we can all agree that YouTube is probably the troll's natural habitat. Like, yes, trolls eke out into other media, but it's probably YouTube first, then Twitter, and then maybe Instagram and Facebook. But you have all been very kind to me as I've been making mistakes, and to each other, even answering each other's questions. So I think that's super, super cool as we're kind of building this academic online community. Also, so again, you can email me, but you can also get at me through the Facebook page. I'll be checking that. And it may be a kind of informal but quicker way to maybe get answers to questions and interact with each other. I post the song of the day up in there too, so it doesn't all have to be business. Comments are seeming like they're pretty done. I think I'll wait another couple minutes, but if not, thank you all for tuning in, hanging out. check out Friday's situation. Email me some questions. Work some homework problems. See if that really weird stuff in chapter 6. Give it a try. Email me your questions. Maybe we can do some stuff later on that business. Anyways, it's been really awesome hanging out. Thank you, everyone who stayed late. We're over our time. But I like to use kind of this time at the end of the stream just to deal with any business questions or other questions, concerns. Yeah. Thanks for hanging out, dudes. I will catch some of you Friday, maybe, or maybe I'll be just working problems if nobody can tune in at that time. But hopefully you can look back and see. And again, with Fridays, I will add an outline to the time. So if you asked a specific question and you don't want to watch the entire stream, in the comments you'll see the time catalog. So it'll be like 00 will be chapter 6, problem 24, and you'll see me work it. 0 or 325 will be the next problem and all that stuff. So it will be hopefully as accessible as possible. Anyways, please let me know how I'm doing. Let me know what your guys' needs are, because I want to be here to meet them as best as I can. Thank you all for listening again, and hopefully I'll see some of you Friday.